All right. So we were talking about Wilsonian RG. And then we started doing the back reaction of the interaction between the fast degrees of freedom and the slow degrees of freedom. Back reaction of the slope. Okay, so we were doing that. So what did we do again? We said there was this S, and we wrote it as S slow plus S fast plus this interaction. And furthermore, this part here, we wrote as S0 fast plus this stuff, right? Which then you just write it explicitly. So there's d to the dx, so there was some 4, that, 6 of this, 4 of that, and 1 of this. Okay? So that's what we have. And then we said what we really want to do is we want to take the, in order to calculate the effective action, so let me write it like this. So e to the minus delta S effective of phi slow is equal to phi fast, all this stuff. Okay? Okay? Good? You agree with that? Because by integrating out the fast fields, you'll get something that depends on the slow fields, and that is really what you want. Alright. So we said the very first part of it was we wanted to find out something that's proportional to phi slow squared. So we have this linked cluster theorem that said basically that if I take e to the v, and I think it's average in some quadratic action, then this guy will look like e to the average plus 1/2 v squared average connected. Okay, this connected just means that it's v squared average minus v average squared. That's really what it is. Alright, so we did this part here, so let's do it again very briefly. So what happened was that part, only this one mattered because you had to have an even number of fields, even number of fast fields. Also, this also has an even number of fast fields, but of course its average does not depend on phi slope. Therefore you throw it out. Okay? So the only thing that matters is this one. So we said that basically the part of this that mattered was minus lambda over 4 times 6 times the integral e to the dx phi less squared of x, and then there was this average of phi greater squared of x. Now what was this? We already know what S0 is for the fast fields, so we can easily do this. That just looks like lambda times 1 minus dl, lambda d to the dk over 2 pi to the d. Right? Now this angular integral is what I call Sd minus 1, and that includes the 2 pi to the d here. So the net result of all this, now this has to be compared to what used to exist in the action, which was just minus 1/2 m squared phi slow squared. Okay? So that tells you that m prime squared should be equal to m squared plus, because this is the same sign as was it appears in the original action. Okay, so this will be basically 3 lambda, right? Because this is 3 over 2, and then the half was there with the m squared as well, right? And then there was this s d minus 1 lambda to the d dl divided by lambda squared plus m squared. And of course, there was something that came from tree level, and that said it's m squared 1 plus 2. Okay, so this was our flow equation. Any questions?
Last part is for loop correction coming from.
This part is the one loop diagram. If you want to think about it like that, so it's sort of like this. is this guy. This is the fast field and this is the slow field. Okay, that's what it is. You've all done finite diagrams, right?
Sir, actually, why the odd number of fields are getting you are including them here?
Because the point is that the odd number of things will not have an average. Right? If I take a quadratic action like e to the minus something x squared and I average x, it will be 0, right? But if I average x cubed, it will be 0.
Oh, okay.
It is really nothing but that. Okay? Yeah, your question.
Because I guess this defines over all configurations average, so that's why the odd powers are cancelled.
Right. Right. So that's the beautiful thing about Gaussian integrals. You can use all kinds of nice properties. Okay, good. So now I said what we'll do is we will define some dimensionless objects. There's that, and then I'll define a lambda tilde, which is a lambda, which is a lambda tilde, and lambda before minus e. Okay. This takes care of the naive dimension of the tuple. And if I do that, then this RG flow equation looks basically like dm squared by dl is 2m tilde squared plus 3 lambda tilde s d minus 1. Okay? Over 1 plus m tilde squared. Okay? That's what it looks like. Fine. I'm going to keep everything to second order, okay, in both m squared and lambda tilde, and I'm going to therefore expand this, and I'm going to say this is 2m tilde squared plus 3 lambda tilde sd minus 1 minus m tilde squared plus other stuff which is higher order, and I'm going to throw it away. Okay, I'm going to keep all the beta functions. This is beta of m squared. Yeah, I'll keep all the beta functions to second order in everything.
But did you ever say that n is perturbatively small?
N is going to be small because we want to be close to the critical point. Right? Otherwise, just, of course, not small. Right? Okay, and of course, we also have to make sure that whatever fixed point we get has m squared and lambda tilde, m tilde squared lambda tilde being small. Right? Otherwise, we can't do this either. Okay.
Sorry, can you repeat what did you say? So what about the, you said something about the convergence properties of that series.
Which one?
Yeah.
Connected.
Oh no.
That-
So his question was like you need n small.
Yes.
Yes.
I need both m tilde and lambda. I'm assuming that they're both small.
Yeah, both small. And for those values, this series, so you are allowed to keep clearly the lower order terms in that series.
That is correct. Okay, otherwise I'll have to keep all these denominators as they are, right? Okay? Eventually, if I find a new fixed point, which we will, I'll have to make sure that the new fixed point also has these guys being small. Otherwise, it won't make sense. Okay?
Small as compared to lambda.
Which validity
No.
of Landau input?
No, now they are all dimensionless numbers.
So is it the validity of Landau input that's your?
No, it's not. It's got nothing to do with Landau principle. Landau principle is valid for large values of m. Okay, I'm talking about m, which is, this m is not dimensionless, right?
Right.
I want it to be much smaller than 1. Okay, that's what I want. Everything is dimensionless.
So which is tantamount to m, not tilde. Just m being small as compared to capital lambda, right?
Correct.
Right. So I mean that is reasonable in some sense. That's
Yeah.
where we started.
It's very reasonable, I agree. But you have to make sure that when it flows, it remains. Whatever conclusions you draw, you better make sure that after it flows, it still remains small.
Otherwise the perturbative framework breaks.
Is wrong. That's right. Otherwise, you'll do something else. Okay? Good. Now let's look at the next term, which we wanted to find. So now I gave you various arguments for why I'm going to throw away various terms here. Okay? For example, this term I'm going to throw away. and that term I'm going to throw away. Okay? Why is that? Because I said that any of these couplings that I have, I've really kept only the low momentum parts of the couplings. Okay? Because when I expanded it out in terms of momentum space, right, I had something that looked like, I really had lambda over 4, so I had dk1, dk2, all these means that, it's d powers divided by 2 pi to the d, okay, I'm assuming all that. So, and then dk3, and then I had basically a constant here times phi tilde of k1, phi tilde of k2, phi tilde of k3, and phi tilde of minus the sum of all the k's. Okay? This constant need not have been a constant. I could have had, for example, some power series expansion. Okay? So maybe I have, something that calls itself something like lambda 0, 0 plus lambda 0, 1 k squared plus, lambda 0, 2 k to the 4th over 2 plus something. Okay, I could have had this whole expansion. Each of these terms is more and more irrelevant than that guy. Right? Because you've added 2 powers of k. So what I really should do is, in order to find out the renormalization of what I call this, I was just calling it lambda, but really it is lambda 0, 0. Okay, that's what I should be focusing on. Okay? So in order to do that, I need to set the external legs of whatever I compute. In other words, the phi slope of whatever I compute, I need to set it to very low momentum. Okay?
So in this expansion, are we assuming that lambda is a function of k?
I'm saying it could have been a function of k. In fact, when you do RG, when you do this kind of RG, this Wilsonian RG, you will generate such functions. Even if you didn't have them in the first place, you will generate all of them.
You could have derivative interactions.
Yeah, but the point is that no matter what you start with, when you do Wilsonian RG, you generate everything. Okay, so you can't help it. It's going to be there. Okay? But what I'm trying to say is that what we really call this lambda is really this guy. Okay, so that's why I'm going to focus upon the low momentum limit of all these things. So this is obviously gone because this low momentum limit, right? In the low momentum limit, this guy, if all of these are low momenta, then this guy has to be also low, right? Because the sum of them has to be low. This is a little bit more non-trivial. Okay, it has to do with phase space arguments. So the point is that if I have this guy being low or even 0, of course you can certainly have 3 of them adding up to 0, right? If they're pointing in some 120 degrees or something like that in 2 dimensions. You can have them adding up to 0. But then the phase space for that is very small, so there's some constraint here.
I'm sorry. I thought these terms anyways drop out because of this eve odd.
Yeah.
A couple of them. If you take
Now I want to now take this term.
Okay.
Okay, I want to take that term. So for the linear term, of course, it doesn't matter. They will drop out. Now I'm talking about the quadratic term. Okay, this term here. So I'm going to say I'm going to drop that as well. Now, I'm going to keep this guy and this guy. And we're going to see that this guy actually will not matter, even when it talks to this guy. Okay, and you will see why. In Wilsonian RG format. Okay, so let's do it.
A in this expansion of lambda, which k is this? I mean, this is the...
Well, so, okay, I wrote it schematically. So the point is that you have to symmetrize it with all the k's.
In all the...
You have to symmetrize it, right? I mean, because these guys are all symmetric, so you have to. So this is just schematic for.
So this third term in that expression. Third.
This.
Right.
Mhm.
So that will give us unset diagram. Right?
Yeah, it'll give you this. In field theoretic RG, this is what will lead to wave function renormalization. But in Wilsonian RG, it doesn't exist. Okay? So this is one of the problems with Wilsonian RG. It's very hard to get certain kinds of things. Okay, so I'll tell you later on how to fix it. Okay? Alright. So now let's look at this V
So
squared.
you are saying this renormalization is different from that is renormalization?
Yes. So the point is that the scheme that you adopt, actually, the fixed point that you get depends on the scheme that you adopt. Okay? So the fixed point that you get for any particular theory depends on which RG scheme you're working with. Wilsonian RG is a particular scheme. Okay, where you take a finite ball of momentum and you start shrinking it and you rescale and shrink and rescale and shrink. That guy gives you all the, it's very easy to think about. Okay, conceptually it's the simplest way to imagine RG. But unfortunately when you actually calculate it, the fixed point contains all couplers. Okay? In the field theoretic RG, the way that high energy people do it, and I'll explain to you why in the long distance limit it actually gives you the same answer. In the field theoretic RG, you keep only 2 or 3 couplers. Okay, so you keep the mass if you want, and you keep your 5 to the 4th coupling. And you still get the same critical behavior. Okay, because it's a different RG scheme. Alright? So you're saying how come? We will see that. Okay? We'll see shortly. Okay?
So that's because these are the only 2 relevant couplings in 4 dimensions. That's why they should be.
No. Okay, so again, when you say relevant and irrelevant, it depends on which fixed point you're talking about. It is true that at the free field fixed point, these are the only 2 relevant couplings. Okay, that is true. But then you should also remember that the position of the fixed point in the space of all couplings is quite different from the directions of the relevant and irrelevant directions. Okay? So the relevance and irrelevance for a non-trivial fixed point has to do with deviations from the fixed point. The fixed point itself in Wilsonian RG is arbitrarily complicated. Okay? It's got all possible couplings. That's one of the disadvantages.
So we have to find normal coordinates at the fixed point.
Correct. You got to go to the fixed point, you got to take the derivative matrix of the beta functions, and you got to diagonalize it, and that gives you the coordinate. We're going to do all of that, okay? We're going to do it. Okay, you guys know too much, so you're jumping ahead. Okay, so let's take it one step at a time.
Sir, but a fixed point is a fixed point. How?
No, the fixed point depends on which RG scheme you use.
No, but the properties.
The critical exponent is the critical exponent. Okay, that's definitely true.
Yeah, so that's what defines a fixed point, right? This spectrum and everything that defines it's a theory.
If you're just patient for one more class, you will find out the answer. Okay? I know exactly what you're asking. I will answer you very specifically. Okay? But let's go through this first. Okay. So now we're going to look at this. All right? Oh, so we're going to look at the square. All right? So let's take this term and that term and square them, and then we'll see what happens. Okay? So what do we have? We have delta S effective coming from this, and this is going to be some functional of phi less, right? It's going to be equal to what now? So this was a plus 1/2 of this v squared, but S effective of course comes with e to the minus S, right? So this must be minus 1/2, right? And then the square, of course the square will have a lambda over 4 squared, right? And then you have this. Now I'm going to write it in momentum space, okay? So I'll say there's a dk1, a dk2, a dk3, and there are 2 powers of this v, right? So there should be a dp1, a dp2, and a dp3. Okay, that's going to be there. Then I have to take the average of something. I'll write down what that something is. The something is 6 times the phi less of k1, phi less of k2, phi greater of k3, phi greater of minus the sum over ki. Alright? There's that plus phi fast of k1, phi fast of k2, phi fast k3, phi fast of minus the sum over ki. All this times some equivalent product in the P language. Okay, so it's phi slow P1, phi slow P2, phi fast P3, phi fast minus I plus a similar term. And then I got to average it over the fast degree of freedom.
So, are you symmetrize the whole, because
Do I need to symmetrize?
no, I don't.
Can I not just call whatever is multiplying phi slow as K1 and K2 and relabel it?
Actually,
That factor of 6 takes care of everything, right? Fine? I don't have to symmetrize. It's only if I had a function of K that I would have had to symmetrize. Okay. So, remember, now there are two conditions. First of all, I only average with the fast degrees of freedom. That's obvious. And I average with the Gaussian action of the fast degrees of freedom. Secondly, I want to make sure that I subtract out the average of this times the average of that. Okay? So how do I make sure of that? The way I make sure is making sure that some field, some fast field from here is connected to a fast field from here. Okay? If that happens, then that will eliminate the average of this times the average of that. Okay? Good. So first, let's talk about why the cross term is not going to matter. Okay, so let's deal with that first. And then we'll actually calculate the remaining term.
So first term and the last term, you basically same.
The last term, yeah, sorry, the one with the phi fast to the fourth power times this. So this is a product, right? This times that average, because there are two powers of your V. Right? Yeah,
Back to that phase space argument.
yeah.
So that means when you take the thermodynamic limit, it goes to 0 because you divide by volume, something like that.
No, it's because the DL,
Yes.
there's a shell, right?
So the shell for scattering is very small.
So the point is that if you have two DLs, so remember when I take a beta function, I just want d by dr. So in general, when I take that the change in something, there will be a DL, there will be a DL squared, and so on. I don't care about the DL squares. So you come with the DL squared. In fact, this term you will see is an explicit illustration of how that works. Okay, there will be DL squared here. Okay, so let's see. Okay, so what I'm going to do, so let's take this cross term. These two guys, of course, are going to be left alone, right? Because they're slow fields. Nothing's going to happen. These two guys are going to contract with two of these guys. And then the remaining two of these guys have to contract with themselves. Okay, there's no choice. Right? This diagram actually corresponds to what you would normally write like this. Okay, this is what you would write. Okay, these are the two slow fields and these guys are all fast. Okay? You understand what I'm saying? Okay, I don't know if all of you have taken Feynman diagrams. You should have. If you have taken quantum field theory ever, then you should know what this is. Okay? But let's write it out. Okay, so what's going to happen is that there's going to be, so there's some factor in front, which I'll forget about for a second. Okay, so there's going to be a dk1, dk2, and a dk3, and a dp1, and a dp2, and a dp3. Okay. There will be a phi slow of k1 and a phi slow of k2. Okay, that much is obvious. Now, I have to pair them up. There will be something called the symmetry factor of the diagram, which depends on how many ways you have of pairing it up and so on. But I'm not even interested. I want to show you that this can be neglected. Okay, so I don't care about the symmetry factors. So what I'm going to do is I'm going to pair it in a particular way. I'm going to take this guy and pair it with K3. I'm going to take this guy and pair it with that. And then I'm going to pair these two guys together. Okay? So, what that means is that, I'm sorry, this was a P1 and a P. Okay, that's what I have. Alright, so this tells me that when I pair the P3 with the K3, right, that'll give me a delta function of P3 plus K3. Right? This is a delta to the D. Right? And then there will be a integral over this guy, but that integral will be only over a shell. Right? That shell will be of thickness dr. Let me just write it, okay? So let me write it as P3 squared plus N squared. Okay, that's this stuff. Right? Then there will be all this stuff here. This combination. Okay? Let me just call it P4, just to make my life simple. So there will be a delta to the D of P4 plus K4. And there will be this P4 squared plus N squared. Okay? And finally, times, there will be a delta to the D of K1 plus K2. Okay? And then there will be a K1 squared plus N squared. And I want to make sure, of course, that all the magnitudes of these guys are sitting inside that shell, because these are fast fields. Okay? So first, let's look at all the delta functions and figure out what's going on. Okay, so K1 and K2 separately added to 0. Okay, so these two guys, if one of them, remember they're both in a shell, if one of them is here, the other guy is here, right? So only one of them has to be in a shell. It's all good. All right. But this tells you then that if I look at K3 and K4, they better be exactly the opposite of each other as well, because K1 plus K2 plus K3 plus K4 is 0. Okay? So therefore I can eliminate one of these guys and call it K3, for example. Okay? So this I can call K3 with a minus sign. Right? Because K3 plus K4 will be 0. So now I will, K3.
How did you get this K3 plus K4?
So the point was that, remember, there was an automatic moment translation invariance condition that said K1 plus K2 plus K3 plus K4 was 0. Right? So that's what I meant when I wrote K4 here. I really meant minus K1 minus K2 minus K3. Okay? But the point is that K1 and K2 together are 0 anyway. So therefore I can replace this by minus K3. Okay?
K3 plus K4 is equal to 0 from the first expression.
Sorry?
From the first expression, K3
Yeah.
plus K4 is equal to 0 because K1 plus K2 is 0 by this delta.
That's correct. Yeah, that's right. So I have P4 plus K4 here. I just call it P4 minus K3. haven't done any magic. Okay. Alright?
So can you please once explain why you put this data function K1 plus K2? And how you get...
Why did I, this one here?
Yes.
Oh, that's because if I want to pair two fields, remember the average of two fields in a quadratic action, they have to have K and minus K. Otherwise their average will be 0. That's just translation invariance, right? Okay? So that's why this has to be 0. Alright? Good? Okay. So now, let's see how many free integrals we have, right? We have one of these guys, right? So certainly these two guys by themselves are going to add up to 0. Right? You agree with that?
Which two is?
Because this one, these two delta functions say that P3
Plus P4
is equal to minus K3 and P4 is equal to K3. So P3 plus P4 will be 0,
Yeah.
right? So P1 and P2 together will just add up to 0. Okay? So that's one independent P. Okay, so let's write it up. So what we have is a dP1, and then I have a phi slow of P1 and a phi slow of minus P1. Okay? That's these two guys. Okay, I've dealt with that. Alright? Then this guy is one of the K1s, and this guy now I will write it out in its full form. So it's 1 minus lambda times 1 minus d up to lambda. D, let me call it K1, that includes the powers of D and all the factors of whatever, right? And then there will be a lambda squared plus m squared, right? That's this guy.
And And there are also properties.
And there's this guy, right? This is a separate integral. Because this integral says delta of P4 plus P3 is 0, right? So then there will be another integral, lambda times 1 minus dl to lambda d, let me call it P3, and again there will be a lambda squared plus m squared, but this time it will be squared, right? Because these guys are the same magnitude. They are the same, in fact. All right? Everybody agree with this? Right. So now you see why it has to vanish. Because it's order dl squared. Okay? So it can't exist. I mean, it exists, but it doesn't contribute to the beta function.
Sir, then 1 by lambda square plus m square whole square is.
How did I get that? So I looked at these two guys. Okay, I did the integral over K3.
Oh, okay.
When I do the integral over K3, this says delta to the d of P3 plus P4 is 0. Okay. So I have two independent integrals here. One of them is P3, because I've gotten rid of this guy and that guy. And one of them is K1. Okay, and of course there is the slow fields which have their own integral, but they have some dependence on phi. Okay? Alright, so this is order dl squared. So it cannot contribute to the beta function. Okay, this is a feature of Wilsonian algebra. So you say, how am I ever going to get wave function normalization in this? That's a mystery. I will let you ponder that mystery before I tell you the answer. Okay? Certainly it's not going to come out in any simple way. Okay? It has to be something complicated. Alright, so you agree that this cross term does not contribute to anything. Okay?
You should drop that.
Which one?
The middle board.
I should do what to it?
No. If you want, you can drop that board. Please don't drop.
First they tell me I have to write below this line. Then they tell me I cannot erase the board.
There are many more boards.
Soon you'll tell me I have to walk on my hands and write with my feet. Okay, so now let's look at the actual terms that does contribute. Okay, now I'm going to keep track of all the factors because this term is going to survive. So it's this times that. Okay? Good. So let's see how many factors there are. So first of all, there is this delta S effective of phi slope. Okay, it contains. All right. So there's a minus 1/2 lambda squared over 16. Then there's a 6 times 6, which is 36, right? And then there's going to be one more factor because when I contract these two phi fasts with those two phi fasts, I can do it in two different ways. Okay? So there's one extra factor. So let me write it like that. Okay? And now I will write down the whole thing. So what does it look like? So as usual, there was a dk1 to dk3, there was a dp1 to dp3, right? And now there was a phi slow of k1, phi slow of k2, phi slow of p1, phi slow of p2, right? And now there's going to be this thing. So let me tear them this way. Okay? So what does that tell me? That tells me that there's going to be a delta function of P3 plus K3 over P3 squared plus M squared. And then there's a delta function of P4 plus K4, and now you know what P4 and K4 mean, right? That's what it is. And then I'll have to put the appropriate restrictions on P3 and P4, like the line that shown. Okay? This would correspond to the diagram. Okay? factoring things yet. Okay, all right. So now let's look at what happens here. So P3 and K3 together give you 0, right? So what do P4 and K4 do? So remember what I have to do is I have to now set the slow fields, the momenta of the slow fields to 0. Okay? So I will set K1 and K2 and P1 and P2 to 0. Right? So what does this tell me? This tells me that P4 and K4, these two delta functions are the same. Right? So there's really only one shaft. They all belong to the same shaft. In other words, let me write it in terms of this diagram. If all these external legs are zero momentum, then the momentum that's flowing in this diagram is P3 and P3. Right? There aren't two different momenta flowing in the diagram. Alright, so they belong to the same shaft. Alright? So that means that what I can do now is I can do the following integral. So let's see what I have here. So I'm going to keep a 1/4 out in front because I have to compare it to lambda over 4 times something, right? So I'll keep the 1/4 outside and then I'll ask myself what else there is. So this is 2 times 4 is 8, that is 9, right? And then I have the following integral. So there's some 3 different integrals, and then there's this guy here, right? So let's write it as d to the dx phi less to the 4th. Okay. But really, you should imagine that I'm taking these at very low momentum. Okay. And then what appears here is that lambda times 1 minus dl to lambda d to the dk over 2 pi to the d, all that stuff, 1 over lambda squared plus m squared squared. Okay, because they're the same. They're the same momentum. If the external legs are the same, are all 0, then these two momenta are the same. Okay? Good?
So these phi less are always small momenta that you are looking
Because I want to renormalize this guy. This is what I mean by it. So you see, I can write a separate equation for this guy, and that guy, and so on. But the equation I'm writing right now is for this guy. That's why I'm focusing on low momentum. If I wanted to write the equation for the second one, then I would take the derivative of this with respect to k squared, and then write an equation for that.
So in general, I can compute the vertex with some finite momentum.
Yeah.
That will give me a k-dependent polarization, with whose whatever continuum limit we are taking, or whatever.
Zero momentum.
Zero momentum.
Correct. We're taking 0 momentum. Yeah. Yeah. Okay? Good? Alright. So let's do this integral. What is this integral? We know it. It's just, this will give me an s d minus 1 lambda to the d dl divided by lambda squared plus m squared squared. Okay? Good? So now we're almost there. Oh, I was not supposed to erase this board, right? Or is it okay to erase it now? I shouldn't have erased that.
It's fine.
It's okay. Okay. All right. So now remember, the original lambda appeared with a plus sign in S effective. Okay. So therefore, let me write down lambda prime. Okay, is equal to lambda times 1 plus dl to the 4 minus e. Right. Remember that? That was its naive dimension. Right. And then there's a minus sign here, and then there's all this stuff, right? So it's 9 lambda squared, the 4 is part of the normalization of lambda, and then s d minus 1, and then lambda to the d minus 4, okay? If I neglect the m squared. Why do I neglect the m squared? Because that's already ordered lambda squared, okay? So All right, very good. Now I'm going to go to lambda tilde, okay, the dimensionless guy. So this says lambda tilde prime is lambda tilde 1 plus dl to the 4 minus d minus 9 lambda tilde squared s minus 1. Okay? You guys agree with that? What happened to the what? M squared. So remember, I'm keeping all the beta functions to second order in all the functions, lambda tilde and m tilde squared. So this is already squared. If I start expanding the denominator here, I'll get something even higher order.
Sir, there will be a
dl. Thank you. dl. Very good. Okay? So let me write down the beta function of lambda. What will it be? It will be d lambda tilde dl, that's the definition. That is 4 minus d lambda tilde minus 9 lambda tilde squared plus d minus 1. Okay? And just remember the other beta function that we had. So beta of m tilde squared. Okay, so there was 2 m tilde squared plus lambda tilde. Was there a 3 here? There was a 3, right? There was a 3 times s d minus 1 times 1 minus m tilde squared plus dot dot dot. That's what it was. Now, I don't like this sd minus 1. Okay, so what I'm going to do is I'm going to redefine a new coupling, which I will call u tilde, which is lambda tilde times, let me even do this, 3 lambda tilde s d minus 1. Okay, let me define that. That's the new coupling. Okay. So here, this will just be u tilde, right? In order to make this an equation for u tilde, I have to multiply by 3 times sd minus 1, right? This will become u tilde, this will become 27 lambda tilde squared sd minus 1 squared, that's just 3 u tilde squared. Okay, so let me rewrite the equations here, and then we'll solve them now. Okay, so here they are. So dn squared by dl is 2n squared plus u tilde 1 minus n squared. Du tilde by dl is 4 minus d, which I'm going to call epsilon. Okay? I'm going to pretend it's small. Okay, so the fixed point that I get will be small in terms of this epsilon. Okay, the epsilon u tilde minus 3 u tilde squared. Right? That's all there is. So it's become very simple. Alright, now we look for fixed points. Okay? So first let's solve this because it only depends on u tilde.
Sorry.
So u tilde star, as the fixed point, is equal to epsilon over 3. Okay? Yeah.
In the second equation, there will be an extra factor of st minus 1.
No. No. That's why I took this. So in other words, in order to convert this into an equation for u tilde,
Yes.
I have to multiply it by 3 times sd minus 1.
Okay. Already that you are multiple. Okay.
Yeah.
So.
Okay. Fine? Okay. So that is the fixed point of that. Now I plug that in here, and I ask myself what value of m star should I choose in order to make the beta function 0. Okay? So it's pretty simple. Here, this is already order epsilon, so I can forget about that when I look for the fixed point of this. Okay? So this tells me that m squared star should be equal to minus epsilon over 6. Okay? Plus order epsilon squared. Okay? Good. Now what I want to do is I want to look at the matrix of perturbations, the matrix that governs the evolution of perturbations around this fixed point.
Sorry, one question.
Yeah.
You talked about that there is no wave function enumeration for this case. Means is there any physical intuition behind that?
No. The thing is that it comes in a complicated way. Wave function normalization in the epsilon expansion is order epsilon squared. Now there are many couplings that are generated in the Wilsonian arch to order epsilon squared. So you have to look at all of those and then you have to somehow fold them into other things and then get the wave function. Just with these two couplings you won't get in Wilsonian arch.
So how we are getting this epsilon tilde renormalization equation? The second equation.
This one?
Yeah.
That's the definition of epsilon. Just look at that. You mean how did I get from the lambda equation to that one? I multiplied this by 3 times SD minus 1. That's all. Okay?
Okay, just a related question. In usual Hypercube, you usually get wave function renormalization even in order epsilon, right?
No,
You don't get.
order epsilon squared.
This is
Always order epsilon squared.
This is not the usual Python.
It's the usual thing. You're not at all unusual. The RG that you're doing on it is unusual, but it's not the theory itself is not unusual. Okay? Good?
One
Yeah.
question. So while writing down the renormalized couplings, you have ignored the terms proportional to DL, which
Yeah.
are higher order in couplings.
Yeah.
So if we look at, for example, this equation, then even if you start with small couplings, they will get big, and so then it is not self-consistent to ignore those terms.
Correct. So I have to stay very close to the fixed point. Okay, if I want to use these flow equations, I better stay extremely close to the fixed point. That's exactly right. Okay? Alright? Shall we now look at what it looks like? Alright, so remember how we went about doing it. So we said basically that if we had dGi by dL was equal to some Fi of all the other guys, Gj, right? And then we found a fixed point, right? Then we said we're going to take Gi is Gi star plus some delta Gi, right? And then we looked for equations of delta Gi. So what were they? So the equation for delta Gi were, first of all, you start expanding in a Taylor series, okay, around the fixed point. But of course the F, where all of these guys are at their fixed point values, is 0 by definition. That's how you determine the fixed point, right? So it's only the first order terms that matter here. And so this will look like basically dFi by dGj at the fixed point times delta Gj, correct? It will be some linear equation. We're now going to find out what that linear equation is. Okay? So, alright, so there's some matrix, right? So what is this matrix? So let me write down the matrix. First, what I have to do is I have to take the derivative of this with respect to m squared. Okay, that equation, and then set everything to its fixed point values. So when I take the derivative, I get a 2 from here, and then a minus u star, right? That's the derivative. Secondly, I want to take the derivative of this equation with respect to u, and then set everything to its fixed point values. So it's 1 minus epsilon over 6 over here. Plus. Okay? Then I'm going to take the derivative of this equation with respect to m squared, which doesn't exist. No dependence at this order. So 0. Finally, I take the derivative of this with respect to u and then set it to its value. This would be epsilon minus 6 u star, right? U star is epsilon over 3. This is minus epsilon. Okay? Now, it's obvious what the eigenvalues are. This guy, because this term is 0, this guy doesn't even count. Right? So the two eigenvalues are, so let me call them lambda 1 is 2 minus epsilon over 3, and lambda 2 is minus epsilon. So you see, anytime you have a negative eigenvalue, it means that the coupling in that direction shrinks. Right? And so this is an irrelevant coupling. Okay, this, of course, is a relevant coupling because epsilon is supposed to be small. So it's irrelevant. So let's draw a little picture and see what's going on. Okay, so here's this is my n squared direction, and that is my u direction. Okay? So we started out here, right? This was the free field fixed point. Okay, everything was 0 there. Then we started flowing away from it, right? And then we ended up somewhere here, right? Because u is at epsilon over 3 and n squared is at minus epsilon over 6. So we're ending up somewhere here, right? So we have some trajectory that flows from here to there. Okay? And now, what we have discovered is that there is one relevant direction and one irrelevant direction. Okay? Fine? So far so good? In actuality, of course, the number of irrelevant directions is infinite. Okay, I just haven't kept those values. As I go to higher order epsilon, in this Wilsonian thing, this fixed point will move out into the space of all couplings. Okay, including U6 and U8 and everything else, and including those things that I erased, you know, the momentum dependent couplings, all those things. They will all exist at the fixed point in Wilsonian energy. So, this guy here is really just a cut through something known as the critical surface. So in the space of all couplings, there is an entire surface, which is infinite dimensional, of things that are irrelevant. So no matter where you start on that surface, you will end up at the fixed point. Okay? So you might as well start anywhere on that surface. Okay, so that's the whole point. Okay, that's what makes the field theoretic RG possible. Okay, and I'll tell you more about that in the next class. Okay, so the field theoretic RG basically says that I will look at the place where this critical surface cuts, actually, maybe I didn't draw it correctly, but whatever. So you will look at that, the place where the critical surface cuts the u tilde axis. And I'll start from there. And you're bound then to go to the fixed point. Okay? So you can start from an infinite number of different places and end up at the fixed point. Okay, that's the bottom line. All right?
You said something about the higher order couplings, lambda 6, u6 or u8 being relevant in its lower dimensions.
Yeah.
Right? And also depending on at which fixed point we
That's
are.
the whole point.
So can you?
So at this fixed point, this by the way has a name. This is called the Wilson-Fisher fixed point. Okay? At this fixed point, the phi to the 4 coupling is irrelevant. There's only one relevant coupling there, and it is what you would not naively call phi squared. Okay? Similarly, if you start at d equals 3, so supposing you start at d equals 3. D equals 3, the phi squared, the phi to the 4th, they're both relevant, and the phi to the 6th is marginal in d equals 3. Now you can do a 3 minus d expansion of a fixed point that has two relevant directions. Okay, you'll have a phi squared, what you would naively call phi squared, and naively call phi to the 4th. But the phi to the 6th will then become irrelevant at that new fixed point. Okay, and then as you go lower and lower in D, you can get more and more fixed points of this type.
So in 2D, how many are
Infinite.
No,
But the point is that the higher you go in those fixed points, the more the number of relevant directions they have. Okay, because this one has only one relevant direction. that doesn't break the symmetry of the model.
Right.
Okay? The one that you start in 3D with 5 to the 6th, it'll have 2 relevant directions,
Right.
and so on. Okay, so you get more and more relevant directions. So they correspond to tri-critical, quadra-critical, or multi-critical points.
So in 3D, phi 6 is marginal, or it
At the free field fixed point.
at the
Always be clear about which fixed point you're talking about. Yes. Right. But at this new fixed point that I'm telling
it's
you,
irrelevant.
it's irrelevant.
At 2D, it's relevant.
At which fixed point?
At the new at the new fixed point.
No,
No.
it's not. That new fixed point travels all the way to 2D. This fixed point travels all the way to 2D,
I
and
see.
it has only one relevant direction. And this is the Ising model.
I see.
Okay, it has only one relevant direction. Okay?
Excuse me.
Yeah.
Lambda 1 and lambda 2 are the Dirichlet eigenspace basically, right? So how do you associate one with n square or the other with the Euclidean?
You don't, right? It's some linear combination of them.
Yeah, so
But it's a relevant direction. Okay, so the only thing you can really say about it is there's a relevant direction and an irrelevant direction.
it doesn't correspond to the previous one, like which one corresponds to the m tilde or the u tilde is not known.
No. Okay, it doesn't correspond to either. It's some linear combination of them. You can figure out what it is, right? Once you have an eigenvalue, you can figure out the eigenvectors, right?
So that means that in actual system you cannot tune one parameter. You have to
Yeah, usually it's called temperature, right? When you have a single relevant direction, you have ordering below some temperature and there's ordering above. Sometimes there are different parameters. Like for example, the other day Samrat was talking about something tuned by pressure. Okay, so you can have different ways of tuning through the critical point. Okay? Good enough? Alright, now let's ask a few more questions about this
Yes.
relevant direction. Yeah.
This works for epsilon equal to 1.
It actually works for all epsilon.
Yeah, so I mean 0 to 1. This
Actually,
is
even up to d equals 2.
up to even big
Yes.
situation.
Yes,
So that gives a non-trivial point in
d equals 2.
D and US.
But of course, the point is that the exponents that you compute here will be some power series in epsilon. So for small epsilon, they'll be good. They'll be an accurate representation of the actual exponents. But then as epsilon becomes big, you'll have to keep more and more terms, and then it turns out this series is actually asymptotic. It's not even convergent. So then there are ways of resumming the series and trying to extract. But at that point, this becomes more of a conceptual tool than an actual calculation or method. Okay? Anyway, in 2 dimensions, we know how to do it much better using control field theory. We don't need all this stuff. Okay, but this provides a bridge between 2D and 4D. Okay? Alright, now I want to look at this fixed point in a little bit more detail. There's only one relevant direction. So let's say I take a very tiny amount of that relevant direction and I ask what happens. Okay? So I'm going to call it delta n tilde square, okay, just for convenience. Okay, even though as Siddharth pointed out, it's not exactly delta n tilde square, but it's the relevant direction. So let me take my delta n tilde square much less than 1. I'm going to ask myself what happens. Okay? Good. So I know that the equation satisfied by that near the fixed point is basically it's growing with that exponent. Okay? Let me just call this some number a because I don't want to have to keep writing 2 minus epsilon over 3 over. So I know that this d of delta n tilde squared over dl is a times delta n tilde squared, right? Where this a is bigger than 0. I solve this very easily. So delta n tilde squared of L is e to the AL times delta n tilde squared of 0, of course, as long as this delta n tilde squared of L also remains fairly small and fairly near the fixed point. Okay? Alright, now I want to relate this to something physical. So now I'm going to wait.
So how are you dropping the U tilde? This is the
No, this is schematic. Okay, this doesn't actually mean n tilde squared.
Modified and new line.
let me call it,
Oh, okay, so this is the
this is the relevant direction. Okay, I'm just calling it m tilde squared because I don't want to invent yet another name. Okay? Fine? Okay, so now, if I go far enough away from here, and yet not too far, because I don't want to go far enough that this whole beta function that I've calculated breaks down, right? I want to stay pretty close to the fixed point. But let's say I'm willing to go up to this guy equals 0.1. That's okay? At that point I'll stop. Alright? And then I will say, okay, if it's 0.1, it's pretty big, and then I can use mean field theory. Okay? Fine? Now listen to this argument. So when I use mean field theory, I get some correlation length. Okay? So let me set the correlation length at that point. So when delta m tilde squared of L is equal to, let us say 0.1. It could be any number, okay? Any number of order 1. Alright? So let's say when it's equal to 0.1, that mean field or Landau-Ginzburg correlation length, it's obviously finite, right? Because it's not at the critical point. It's some number. Let me call it C1. Okay? I don't even care what number it is. But now I ask myself, what is the correlation length then when I started? Okay? So in a Ginzburg-Landau theory, with this value of delta m squared, the correlation length is C1. Now, how did I get here? How many times did I rescale in order to get to this particular value of L? So the length scale by which I have rescaled is e to the L. You agree? Every time I rescaled it, I said x prime was x times 1 plus dl. I do it n times, right? It becomes e to the L. Right? So that tells me that the actual correlation length where I started is actually equal to this finite number times e to the L. Okay? Good enough? Alright. But now I also have delta m squared of L is equal to delta m squared of 0 times e to the AL. Right? So therefore, this delta m squared of 0, this e to the L, is going to be equal to delta m squared of L divided by delta m squared of 0 to the 1 over 8. You agree? Alright? So this is C1 times delta m squared of L is 0.1 according to what I've chosen, right? This is delta m squared of 0 and this is 1 over 8. Okay? So this tells you how your correlation length depends upon the deviation from the fixed point. Okay? So this tells you that this delta m squared of 0 is something that's proportional to t minus tc. Okay?
So what was the last argument? How did T minus Tc come out?
How did t minus tc come about? Okay. So if I'm exactly at tc, then I'm somewhere on the critical surface. Okay, I don't know exactly where. But very soon, because everything on the critical surface goes towards the fixed point, very soon I come to the fixed point. Okay? So let's say I'm somewhere here. So I cross it like this as I change t. Okay? So when I'm here, I come to the fixed point pretty quickly. Now let's say I deviate very slightly from it. So pretty soon I come here and then I start flowing out along this line. So I'm only looking at that long RG time when I flow down here. Okay? So that's all I'm counting. So this tells me that this must be some constant. So let me call it C1 times T minus Tc to the minus 1 over 8. All right? But the definition of the correlation length exponent was exactly that this guy should have been mu. Okay? So now we are ready to calculate our very first correlation length exponent, right? So this must be 1 over 2 minus epsilon over 3. That's what it is. So let's just make a quick check. When epsilon is 0, we are in 4 dimensions, and we know that mean field theory is correct. So it's 1/2, and that's correct. That was the value that we got from that. Now, let's say that we want to go to t equals 3. So we had epsilon equals 1, so it's 2 minus 1/3, so that is 5/3, so this is 3/5, 0.6. So it's different from a half. If you actually go to the Ising model and solve it numerically, you'll find it's 0.67. Okay? So this is not quite right, but certainly trying to go from the mean field to the correct one. Okay? And if you go to higher ordered epsilon, which I'll tell you how to do the field theoretically next class, then you find that it gets better and better for a while. But then after a while it becomes worse because it's asymptotic. Okay? So you don't want to go too high in epsilon, powers of epsilon. Okay, so that is the connection between this eigenvalue here and the critical exponent mu. Okay? Right?
Could you explain 2 points again? This, how many times has rescaled is e to the power L?
So remember, every time I do a little dl, imagine I do it discretely, okay? Imagine that my dl is not infinitesimal, okay? Let's say I want to scale by a factor of 2, okay? I divide up the factor of 2 into, let's say, 100 parts. Okay, so each dl is going to be basically log 2 divided by 100. Okay, and then I do it 100 times. Each of those 100 times is a little dl. Okay, so that's what I'm doing. Okay, so that is why this is the scale by which I have rescaled.
Because lambda prime with lambda is just dl.
Precisely.
So you are doing e to the power sum over d.
Correct, exactly. So if I wrote something that looks like d lambda by dl, right, that would actually be minus lambda, right? So that's exactly what it is. But lambda is a momentum scale, so the length scale grows. Okay? Good?
But when you, what is L0? Then this del m square 0. What is 0 for you?
So the point is that's where, in the Bayer model, I'm very, very close to the critical point. Okay, so in the Bayer model, I'm starting at L equals 0. Okay? So that's what I was saying here earlier. So in reality, of course, you never start at the fixed point. The fixed point is something very complicated. A general model will never actually touch the fixed point. But in a general model, as you tune some parameter like temperature, you will cross the critical surface. Okay, remember, this is some infinite dimensional surface.
You asymptotically kind of go down, right? You can't intersect it like
Right. So what happens is that, so let me draw another picture, a better picture. So this is the critical surface, okay? It's infinite dimensional. On this critical surface, there's a fixed point. So this critical surface is some infinite dimensional surface. On the surface, there's some fixed point. There's some relevant direction. And this is behind the critical surface, okay? Now, your general parameters will take you across the critical surface. So let's say below is the ordered phase and above is the disordered phase, okay? So now, if you're sitting exactly here, then you see there is some irrelevant direction that will take you into the critical point. And the argument is that this is going to take some finite amount of time and then RG time. And then you'll be very close to this guy, right? So most of the time, if you are slightly away from the critical, then what's going to happen is that as you flow, you will flow here. You'll of course also be flowing slightly away along the relevant directions, right? And then it will get closer and closer to this direction. which is the purely relevant direction, because all other directions are shrinking, because they're all irrelevant, right? So you're going like that, and so therefore you might as well have just started from here. Okay? And that's what I'm doing over there. Does it make sense?
And the second thing, this fraction, replacing it by t minus tc, could you explain that?
T minus Tc, this thing here.
Yeah, what?
So I'm replacing delta m squared of 0 by T minus Tc. Okay, that's all I'm doing. Because I'm saying that whatever is doing it here, right, unless you do something fine-tuned, it's going to be just something proportional to T minus Tc plus something proportional to T minus Tc squared and so on and so on. Right? If you're tuning a parameter and you hit the transition, unless you really fine-tune it, it's going to hit it linearly. Right? So that's why this distance over here is proportional to T minus Tc. Now I'm saying I'm going to replace that by that distance over there, because as far as most of the flow is concerned, it happens along this line, along the relevant direction. I don't need to worry about what happens along the irrelevant direction, because they always bring me to the fixed point. Okay? Fine?
Sorry, how do you define your critical surface?
How do I define the critical surface? So, imagine that I have some model that has all possible couplings, okay? And then there is some fixed ratio, and I change one parameter, okay? It will cross the critical surface, typically, right?
It will cross what?
The critical surface. So there will be a phase in which it is, you know, so for example, I can take, so just let me give you a specific example, okay? So let's take my two-dimensional Ising model, right? I can certainly have a nearest neighbor coupling, which I will call J1, right? I can have a second neighbor coupling, which I can call J2. I can have a four-spin coupling, right, around a plaquette that I can call, I don't know, J plaquette or something. So there will be J1, there will be J2, J3, and then there will be J plaquette, and there will be all kinds of other couplings, right? Now imagine that I fix the ratios of these couplings, and now I have a temperature, right? And as I change the temperature, at some point this model will order as I reduce the temperature, okay? So that's one point on the critical surface. That's one point on the critical surface. Now I vary all these guys, and I map out the critical surface by just varying all these guys. You can see there's an infinite number of possible interactions, right? So I'll have this infinite dimensional surface on which it's really Ising critical. It's really an Ising model criticality. Because all these points on that critical surface will go towards the fixed point. Okay? And when I deviate from that critical surface, the critical behavior of that will be just the Ising critical behavior. So it doesn't matter which of these models I work with, it has the same critical exponent. Okay? That's universality. Okay? The presence of the fixed point is what tells you that models that are microscopically different but have all the same symmetries will actually have the same critical exponents.
But if you change this J1, J2, J3, like so the fixed point also change.
No. The fixed point depends only on your RG scheme. Okay, the fixed point depends on the RG scheme. So let's say you apply the same RG scheme to many different models. Okay, well, at criticality they will all flow to the same fixed point. Okay?
Value is same for all these.
Sorry?
The value of the critical, this U tilde and epsilon tilde, the value at the critical point is same.
Of course. So I'm playing a dirty trick on you because the point is epsilon expansion at low orders than epsilon, only a few couplings are important. But in the Wilsonian method, as I go higher and higher order in epsilon, I have to keep more and more couplings because they get generated even if they're not present in the first place. Okay, so in reality, in the Wilson-Fisher fixed point, all couplings are present. Some of them are very small. If you do it in epsilon, some of them order epsilon to the 15th, let us say, right? But they're there. But the claim is that every model every Ising model will flow to the same fixed point if I do Wilsonian arrangement.
So then you have the all couplings are there.
Correct. Yeah. Yeah.
So if I'm an experimentalist, I
Yeah.
don't know about archetypes.
Yeah.
So then how do I go to the fixed point? How do I tune? How do I know what is the control parameter which takes me to the
Temperature, usually. I'm talking about an Ising model, right?
no, but or a general model, how do I know?
You don't. A general model, you just vary all parameters and you see what happens. Right?
So basically this term is actually just a first order change because you're taking a small tuning away from the
What do you mean by first order change?
this linear term, this t minus t, this 1 by del n square.
Yeah.
This is proportion to only first t minus t, see not the higher order correction, right?
But I'm talking about very tiny key by
Yeah,
yeah,
exactly. That's what I'm saying.
Yeah.
You're just moving very slowly away from this little distance.
The point is that the critical exponent is defined like this. Okay, so you have to be really close to the critical point to measure the critical exponent.
No, suppose even in this model, and
Yeah.
let's forget that we know anything about Ising model. I'm a blind experimenter. Okay. So I apply some temperature magnetic field, right?
Okay.
And I apply both of them at the same time.
Okay,
How do I know which one is the control parameter?
they're both control parameters. Because
But
control
I-
parameter is something you can change in the lab.
Yeah,
That's what a control parameter
I'll
is.
get a transition if I change one, and I'll not get a transition if I change the keeping the other fixed.
Correct.
If I change the magnetic field, I'm not going to get any transition.
You will get a first order transition if you're below the critical temperature. Yeah, you will get a whole host of phenomena, right? You'll get lots of phenomena.
In other words, there can be so this M is a bit misleading. You can call it some other thing, P or something.
Call it whatever you want,
Right.
it's the relevant parameter.
Right, but an experimentalist does not know what is the relevant parameter to begin with.
Look, if you don't know anything, if you insist on not knowing anything, then of course you will end up also not knowing anything. Okay? You have to assume some knowledge, right? You have to assume that you know what symmetry.
Yeah, so there is a first order correction, so it can be a linear combination of T minus Tc plus something. We can keep only till the first order.
I don't understand what you guys are saying about first order at all. Okay, that's not correct. That is not correct. So what I'm saying is that typically when an experimentalist makes a measurement on an Ising model, so he or she will put the field to 0. Because you know that if I have the field on, then there's always a magnetization, there's no transition. Okay, there's no free energy singularity. Alright? So you make sure your field is 0, then you change the temperature.
Yeah, but the experimentalist does not do an experiment on the Ising model.
Okay, you tell me the system in which you do it. If you're not going to tell me anything, how am I going to tell you something?
Some magnetic insulator.
Magnetic insulator.
Right.
Okay.
Okay.
You're bringing metals and insulators into this?
No, it can be described by Ising model. Basically, I'm telling you a system which might be.
Okay, so it can be described by an Ising model.
Yeah.
Okay, then you told me there is an Ising model. So, look, I'm not able to understand your problem. Okay?
There are more than one tuning parameter.
Okay, so the point is, look, there could be a fixed point with two relevant directions. In that case, there will be two tuning parameters. In fact, the Ising model is of that type. If I am allowed to break the symmetry, then I have to tune both H and T. Okay? But supposing I'm assuming symmetry, this holds for a lot of magnets, right? If you don't put them in a field, then there's no external thing that breaks the symmetry. This is, look, you have to know something, okay? And then you say, okay, then given the fact that the field is 0, I have to change only one parameter, and you see the transition, right? If it's a tri-critical point, you'll have to tune two parameters in order to see the point, right? If by varying just one parameter you can see the transition, then you know that this fixed point has only one relevant direction. Then you know that no matter how you traverse that transition, you'll always get the same critical exponent. Okay? So I'm not sure what all this first order or second order
No, okay,
business
so
is.
let me
Okay.
simplify the thing. So we started with an M, a bare M,
Yeah.
right? So that, for us, that was T minus, so that M was being generated because Like
Yeah.
we were away from some critical point.
Correct,
That is T minus Tc.
correct.
M square is T
Yeah.
minus Tc.
Yeah,
Okay, now
it
you
still is, it still is.
Yeah, but point is that this is not M, this is some combination of M square and U tilde.
Doesn't matter.
The U tilde part does not matter.
No,
Whatever.
the point is this, you're crossing, so look, your actual model has all kinds of couplings, okay? Not just the phi square and the phi 4. It got everything in it. But it crosses the critical surface at some point. That's all that matters. Okay? So if you're on the critical surface, you flow to the point, the fixed point. If you're not on it, you have a bit of a relevant direction. You can call it whatever you want, okay? But this T minus Tc has overlap with that relevant direction. Otherwise, you wouldn't be able to see the transition by changing T. Okay?
Can you repeat this statement J1, J2, J3, J5?
So the question was, what is the critical surface? So I'm saying you take some Ising model, it's got all these things. Let's say this is 10, this is 2, this is 1, this is 5, whatever. And then I change the temperature. And then I find that it undergoes a transition at some point, at some temperature, right? So that has mapped out one particular point on the critical surface. Now I change the ratio of these guys and I do it again. And I map out another point on the critical surface. Then I go to my nearest neighbor Ising model and okay, so the point is that if I think of this J1, J2, J3, all these as different axes in some multi-dimensional space, there is some surface, right? For small j's it is disordered, for large j's it is ordered. So there's some surface that bounds the ordered region away from the disordered region. That is the critical surface. As long as I don't break the Ising symmetry of plus going to minus. Question?
Yeah. What defines the universality? The critical surface or how many relevant directions there are?
Universality occurs when there's a single fixed point on the critical surface. Okay? If there's only one fixed point, then there's universality. Because no matter where you start from this critical surface, you have this fixed point. And then when you cross it, you end up almost at the fixed point but slightly away. And then the correlation length is going to be given by this relevant direction. Okay? You can have universal tri-critical points also. Points where there are more than one relevant direction. They can also be universal. Okay, they may have more relevant directions, but they still have a critical surface, infinite dimensional critical surface. Critical surface is a set of all irrelevant directions.
So all the Ising universality class systems will have same critical surface and same number of relevant directions?
Yes. Yes. Yes.
But the fixed points may be different. A critical point may be different.
No, depending on what dimension you're in. If you're in 3 dimensions, you're talking about the 3-dimensional Ising model, there's only one fixed point. Given your RT scheme, there's only one fixed point, there's only one set of critical points. Okay?
If there is suppose more, if you allow more coupling, you will get suppose another fixed point. Is it telling that the relevant direction, whatever it is, it have to end at that fixed point or it may not end?
No, remember, we already had 2 fixed points here. Right? We had the
Yeah, this
Field
is a
fixed
fixed
point
point.
and we had the Wilson-Fisher fixed point. So we already have 2 fixed points. Okay? So the thing about the Ising model is, this fixed point has 2 relevant directions without breaking the symmetry. Whereas experimentally, I know that in the Ising model, I have to tune only one parameter to have the transition. So I know this cannot be the fixed point that describes the Ising model critical point. I know that. So I know I'm looking for a fixed point that has only one relevant direction.
And where do those lines end? I mean, because where do those the relevant lines?
The relevant lines go away. So the point is that there are 2 other fixed points which are sort of trivially scale invariant. One of them is an infinite temperature fixed point, where the correlation length is 0. Okay, so if you rescale 0, you still get 0, right? The other one is 0 temperature fixed point, where the correlation, I mean, everything is just ordered. Right? So nothing can change when you rescale. But those are kind of trivial fixed points.
So they end in one of.
They end in 2 different fixed points.
But if we had another fixed point, then they would go and hit.
Absolutely, yeah. We know of situations where there are multiple fixed points. Yeah. Yeah.
Suppose I'm taking an Ising model with all infinite range hopping, and then
As long as it's not terribly infinite range. I mean, you can have infinite range but suppressed exponentially.
yeah, so then
That's fine.
That's
It
fine.
still belongs to the same class.
Okay, so there is a cutoff.
It's not, no. What I mean is that there's a difference between power law interactions
Yes.
and exponential interactions.
Okay.
So power law interactions, if you go slower than some power, it can change the universality class. Okay? But exponential interactions are equivalent to short range.
What about random?
Oh, that's different. Very good.
So
Random anything is very different. If I have random bonds, for example, random bond Ising one, that's very different from this. Okay?
So the scheme is like will work for all these type of models like this Wilson Fisher scheme.
It will work for translational invariant models.
But not
For random models, there's something else. But it's some, I mean, it's much more poorly behaved. There's some 5 minus d expansion that you can write down for random bond models. But that's poorly behaved compared to the Wilson-Fisher functional expansion. Okay? And then there are other special things you can do in D equals 1 for random models, which are essentially exact.
I'm staying within some scheme. And what can we say about the goodness of the scheme? Like if I change some other, if I went to some exact scheme.
You have a talent for very vague questions.
Suppose I could do this exactly to all orders. I thought about another fixed point. So can I say anything?
So what do you mean? You mean you can do this epsilon expansion to all orders? What can you do to all orders?
I can calculate, I can do the expansion to all orders.
Okay,
Yeah.
so then you'll find the exponents to all orders. But what's the question? What is the question?
No, so I got some fixed point staying within this Wilson-Fisher scheme.
Right.
The question is that if I did use some other RG scheme, is there a guarantee that this only going to be this, or there can be some other fixed points? After all, this is a perturbative scheme.
So let's ask whether you're willing to stay within the regime of short range interactions. You're willing to stay within the 5-foot theory. Let's say you want to start from the 5-foot theory, and then you want to ask, are there fixed points other than the Wilson-Fisher fixed point? Is that the question?
Right.
To answer that, you have to do some numerical stuff. Okay, so the point is that if your lambda, for example, initial lambda is very big, right, then you can't do perturbative stuff. But numerically, it's actually known that this is the only fixed point with one relevant range in the 5-foot theory. Okay. Now, that's the Ising model. Now, if you do some other models, then there can be multiple fixed points. Okay, and you can get them all even within this. So then the conjecture is that if you do something more precise, more numerical, there are numerical ways of doing RG then. Okay, so you can do that for things that are not perturbative, and then you can try to map out the different fixed points there, and some of them may be non-perturbative.
So those cannot be accessed via this.
Not by this method. But RG is a concept. It's a way of thinking. Okay, don't identify RG with this. There's RG and then there's a particular scheme of renormalization. Right? So this is one scheme which actually has huge power because it applies to a huge range of theories. Okay? But there may be some theories to which it doesn't apply. And then you have to try something else. But this way of thinking is very powerful.
So, what do different fixed points mean? Do they mean that you have different phase transitions, or are they?
Yes.
So, yeah.
Yes. It means that there are different phase transitions, different universality classes. Okay? So previously what people used to think was that given two phases, two distinct phases, if there's a second order phase transition, then the critical exponents are unique. But very recently, examples have been found where the two phases are the same on both sides, but there could be different transitions. Like qualitatively different transitions between them with different exponents, different everything. Okay, so,
So, but then how do you define the phases? I mean,
no, the point is the phase transition may not be described completely by either of the phases. That's the whole point. Okay, so normally we are used to thinking that the phases define the phase transition, right?
right.
Because, why is that? Because we are used to thinking that the degrees of freedom that are important at the phase transition are basically slow fluctuations of the order parameter. That's what we are used to thinking. But there are certain phase transitions where that's not true. Okay, where there are degrees of freedom that emerge, which are not contained in the theories on either side. Okay? So, it can happen, but it's a very exotic phenomenon.
There is no order parameter. There is no order parameter.
No, you can have order parameters, but the degrees of freedom that appear at the phase transition are not described by the order parameters. They're something else. Okay, that can also happen.
So, can you give an example?
Yeah, there's this whole phenomenon of deconfined criticality. Have you guys heard about that?
Yes.
So that's what that is all about. That you cannot describe the critical point in terms of the order parameter fluctuations on either side. You need some new degrees of freedom. Okay. All right. It's getting late. So tomorrow I will tell you a little bit about the field theoretic RG. I'm not going to go into detail because that's